Alright, so definition 2. If the only divisors of a natural number p are 1 and p, or p does not equal 1, then p is said to be prime. We give some examples of prime numbers: 2, 3, 5, 7, 13, 11, 13, etc. Familiar prime numbers. We note that 2 is the only even natural number that is prime. Every number that is prime has exactly 2 factors, namely 1 in itself. And the consequence of all of this is that, 2 is the only even prime number. We can think about that very easily when we think about all the other even numbers, for example, 4 and 6 and 8 and so on. 4 is necessarily divisible by 2. Every number that's divisible by 4 is necessarily divisible by 2. And each such number would have exactly, or at least 3 factors, right? That would be, as we said, 2, 4, and itself, and 1. So you're going to have greater than 2 factors every time in such cases. If a natural number n that does not equal 1 is not prime, then we say that it is composite. And it's kind of an interesting observation to make that, of course, prime numbers are also composite. I mean, they're composed of 2 numbers every time, 1 in itself. And so each such number that is, I suppose, composite but prime would be just considered composite, such as the even numbers greater than 2 that we discussed previously. Axiom 1, every non-1 natural number, or every not 1 natural number, that is an element of the set P or C prime or composite. Just a little bit of set notation there, set theory notation. Composite numbers may be factored as products of primes, as in 36 is equal to 2 times 2 times 3 times 3. And then we have a factorization tree, a prime factor tree. And these diagrams are pretty easy to make in Pages. They're just little text boxes, right? I can go and I can ungroup it so we can see what exactly it is. So just little text boxes, and then very small lines. And then you can adjust the line width to your preference and so on. So that's quite convenient. Theorem 1, the fundamental theorem of arithmetic, states that every natural number has a unique prime factorization. Every natural number has a unique prime factorization. Irrespective of the incipient expression, every scheme leads to the same prime factorization. Consider the 2 distinct approaches for obtaining the prime factorization of 72. So what do I mean by incipient expression? This first expression here, to the right of the equal sign. As long as it's, of course, valid as a multiplicative expression that factors to the, I guess I might say, root expression. The number of interest, whether it's 72 in this case or whatever else. So irrespective of the incipient expression, every scheme leads to the same prime factorization. both of these schemes factor to this prime factorization, or reduce to this prime factorization. Ultimately, the result is uniform, right? All right, 0. If we add the element 0 to the set of natural numbers, we obtain a new set of numbers, which are called the whole numbers. These are our whole numbers. The natural numbers, counting numbers, with 0. And then we take it for granted the fact that, or the notion if you prefer, that division by 0, any whole number divided by 0, returns or means, yields, right? Yields nothing of meaning, lorem ipsum. It's meaningless. So we'll consider it a self-evident notion that division by 0 is meaningless and therefore undefined.